Hello everyone, my name is Gregory Lane from Bristol-Myers Squibb, and today I'm going to give a presentation on real-time monitoring of downstream biologics operations. Now a little bit more about myself. I am in an engineering technology department at our New Brunswick, New Jersey site, and we focus primarily on process analytical technology and other techniques to gain understanding in real time of various processes and drug products and drug substances under development. Here's an outline of my presentation today. I'm going to start off with an introduction to biologics operations. And really what I want to convey here is the overall upstream-downstream continuum, as well as the driving force for using process analytical technology. Since the seminar is sponsored by METTLER TOLEDO AutoChem, I'm going to be focused on one of their main products, the FTIR spectrometer, and how one can use that to take trends and generate trends in aqueous-based systems. So peak trending and FTIR in water will be a big part about the presentation. And then I will move on to one technology to rule them all. It's just one slide. It's probably my favorite slide in the presentation because there are multiple species that can be trended in a downstream operation. Yet each one of these species, analytes of interest, would require a separate analytical technique. Yet by clever use of the FTIR spectroscopy, you can trend three different things all at once. We'll move on to some advanced modeling. This is more or less PLS modeling. I won't go into great detail about PLS modeling, but I'll show you how it can be used to generate quantitative information on different analytes of interest. And then we'll finish with a single conclusion slide. So here's an overview of biologics operations, the upstream and downstream continuum. The diagram comes from Repligen, which makes a perfusion reactor, which is something that actually goes adjacent to a bioreactor. It results in high cell density processing. But the real driving force of all this is we start out with higher protein concentrations, and that in turn has to be isolated and purified, and some of this is even continuous. And then as a result, you go downstream to the drug product formulation, which is where I spend a fair amount of my time. And again, we are seeing throughout the biologics continuum higher titers, higher concentrations of protein, and a need for greater throughput. All of this is driving the need to have process analytical technology to be able to monitor these things in real time. So here's an example of tangential flow filtration, another partner company we work with, Pendatech. That diagram is from them. But the principle is fairly straightforward. It relies upon a membrane, and I will describe this membrane in greater detail on the next slide. But basically the process is you have your protein in one tank. It cannot penetrate the membrane. And then you have a buffer solution in another tank, or a gravity fed, and you put it in the main tank, and then it just circulates around in the system, around and around, and the buffer you don't want comes out. The protein is retained in the system, and then the buffer that you're exchanging into goes through the system, and it's just a simple diffusion type process where one species or multiple species leave and new species come in, and then at the end you end up with something, a new formulation or a new drug substance in a platform type buffer. So let's take a closer overview of the TFF membrane in this diagram of the membrane. So what we start out with is a protein solution that can readily pass along the membrane but not permeate through, whereas small molecules can permeate through and end up in the filtrate. And when I say permeate, I say readily in quotation marks, because in theory you would use a certain number of diavolumes to exchange one excipient for another, but we've noticed some non-ideal effects at high protein concentrations. And this is really why you want an FTIR in there, so you can monitor what's going on in real time. So let's talk about FTIR spectroscopy in water. Historically, water has proven to be a challenging system for using an FTIR spectrometer because the cells that were used to measure the system typically had longer path lengths, and the water itself would absorb so much of the infrared signal that it was difficult and challenging to pick up the analyte of interest. However, and I'm going to give credit to the right side of my slide here to Jim Cronin and Tyler Gable from METTLER Toledo Autochem. They provided this portion of the slide. METTLER has designed a probe system called the silver halide probe, and the most important feature is the ATR, attenuated total reflectance window. What happens is the signal only penetrates a few microns into solution. So therefore, you don't have a long path length to try to overcome, and more importantly, you are still absorbing some light due to the analytes of interest, and that signal is making its way back to the detector, and you can see what's going on. It is true that even with this system, yes, there is a strong water absorbance signal. However, as long as the analytes of interest are of sufficient concentration, you can still pick up meaningful peaks that you can trend in real time, and I will show that over the next few slides. Moving on, we can see that despite there being a large water absorbance, as shown here in the magenta or pink, as long as you have sufficient concentrations of material in solution, you can still pick up these peaks. So shown here in purple is some sucrose and also a protein in green. Now do note that most proteins have some form of sugar in them to help stabilize the protein solution. But you see here on the left there's very distinct peaks due to protein-related stuff. On the right there's also very distinct peaks due to sugar-related or sucrose-related in this example. And with that said, you can then trend some of these things in real time, and I will show you on the next slide how we can even get rid of the water background if we so desire. So here's an example of water subtracted from the spectrum showed previously. And naturally, water subtracted from itself is going to give you a flat line. But then when you subtract it from the protein-based solution, you see very distinct peaks. Over here are what called the amide 1 and amide 2 peaks. Over here on the right are sucrose-related peaks. I'm not going to get into too much detail about peaks and peak identification, just because what really we're interested in for this presentation is how to take some of these peaks and then trend them in real time. But for those of you who like taking a closer look at peaks, you can do that with the software that's built into the METTLER FTIR system just by subtracting out water or other species and then see what's left behind. So here we can see some peak trends from an ultrafiltration process. What's going on here is we're using two different peak trends, one for protein, shown in orange, and then the other for sucrose, shown in green. The process involves basically removing buffer and water from the system, and as a result, the protein signal goes up over time, and then we add a fresh batch of more dilute protein. So we're starting at 50 mg per ml approximately, and then since these peaks are normalized, 0 is the low point, but this would be about 33%, somewhere up here is 66%, and 100% would be your highest concentration of protein, and likewise for the sucrose peak. And what we see is the protein does get more concentrated, gets diluted when we add more of the 50 mg per ml solution, and then it keeps getting concentrated. You notice it also slows down over time, which could be, by the change in the slope, you see it's a little bit longer, could be due to protein actually building up on the membrane. If you look carefully at the x-axis, you'll see this is essentially an all-day process. It was effectively about 6 liters of protein solution being concentrated below 2 liters, down to about 1.5 liters. We also see some changes in the sucrose levels according to the peak we're trending. These aren't big changes because we're not really exchanging any sucrose levels. However, there is a apparent slight decrease as the protein gets more concentrated, and that's an interesting phenomenon we'll probably cover a little bit more in another slide. So let's take a closer look at another variation of TFF called diafiltration. And in this example, we are starting with a known concentration points of our protein and our sucrose, actually. And what we're doing is we're using the FTIR software, and Jim and Tyler can teach you how to do this, but we're using known points in the process, and then we're going to use that to trend semi-quantitative trends throughout this particular diafiltration. And we're removing low levels of other excipients, as well as trying to get the protein sucrose mixture into a 250 millimolar sucrose buffer. And the axis on the right is for the sucrose in millimolar, and the second axis over here is the milligrams per ml. That refers to the protein. So let's just take a closer look at sucrose. This is my known point, so I can define this point in the FTIR software. And likewise, I know here I have a starting point for the protein of around 165 mg per ml. So let's follow the protein trend first, and then we'll talk about the sucrose. You can see right away, early in the process, we decide to dilute it with some buffer. What's going on here is it's too viscous. It's too concentrated. We can still run the process as is, but it would probably take far too long at this high level concentration. So we dilute it, and that's pretty clear. And then at the end, the strategy is you concentrate it again by reducing the volume. And then finally, we see right here, this is another increase in concentration. This is not because of anything we did in the TFF. We actually took the protein out of the tank, mixed it in a bottle, because it was so viscous, and you could clearly see the stuff was not 100% mixed. And then I put the probe back in there to get a value for my protein. And we were estimating 196 mg per ml here. And then what we ended up with an offline UV vis analysis was 193 mg per ml. Similarly with the sucrose, we try to reach 250 millimolar, which is our buffer we're exchanging into. You notice we never get there. We did not have enough driving force. And this is the phenomenon we see when we do these types of TFF operations, the diafiltrations. And this is why it becomes so important to have the FTIR in the system, because it's sort of a guessing game. Do we need 250 millimolar? Do we need 280? We don't really know. We want to be at 250 millimolar at the end, but we never quite get there. The other interesting phenomenon, and I hinted at this before, is what we call a volume exclusion effect. As the protein gets more concentrated, the sucrose actually appears to get excluded from the membrane system. In other words, it's actually getting pushed back out of the system, and it actually drops lower. And I think what we end up with from our chromatography analysis is we were predicting 219 millimolar sucrose, and the offline chromatography analysis gave us 218.6. And that's a published paper, but it's a difficult chromatographic separation. It requires capturing the protein on a guard column and then pushing the sucrose through and detecting with a CAD detector. Again, it's a known reference in the literature. We have it. It was published by BMS scientists, but it just shows you how tricky it is to run a process like this. But with the FTIR at your disposal, you can take advantage of defined points in the process and do semi-quantitative trends and learn something about what's going on in the process in real time. So that's the big advantage of using an FTIR in the system. Here's another example of a diafiltration, and this is the slide I titled earlier, One Technology to Rule Them All. In this particular example, we're starting out with a sucrose in the mixture, and we are removing that by exchange, and we're basically exchanging this into a phosphate buffered saline. And we see a very interesting phenomenon. Now, again, to get these types of trends, this is not so much semi-quantitative as the prior slide. I have to carefully pick peaks, and I have to use some spectral pre-processing, so I use second derivative pre-processing. But what I can see is a very clear peak for the phosphate buffered saline, and by the way, this is actually phosphate buffered saline added to the system, so I know where that peak is showing up. And then I add the protein containing the sugar in there, and you can see as we exchange over time, the sucrose comes down, the phosphate buffered saline concentration goes up, and then the protein concentration goes along for a while. These are normalized peaks, not semi-quantitative as shown on the prior slide. And then at the very end, we concentrate. Interesting phenomenon. We don't know if it's 100% real or not, but you see a slight up increase in the concentration of the phosphate buffered saline. That's believed to be real because sometimes proteins, especially if they're positively charged, can pull over a negative species, a negatively charged species. So we think the phosphate is coming across the membrane and actually being retained somewhat. But again, the way you would prove that is to go do an offline analysis. What really counts in this slide is you're seeing 3 different materials that would require 3 different detection techniques in order to pick it up. Now, if you were just focused on the protein itself, you could use UV, you could take an offline sample, or I mentioned Repligen earlier. They bought a company called C Technologies. They make a thing called the Flow VPE. That's an inline UV vis spectrometer, and that would be able to trend this in real time. But if you wanted to detect the sucrose, you would have to take a sample and pull it out and then analyze it, typically by chromatography. There are other techniques, but the way we do it at BMS is we actually take it, it's separated from the protein on the column, and then the sucrose levels are quantitated. That's a published paper. We can get you that if you're interested. And lastly, the phosphate buffered saline, that's a totally different species. That would require probably an ion chromatography to accurately identify and quantitate. But here we are trending all 3 at the same time, which is what I think really makes this a powerful technique as far as downstream or upstream operations are concerned. As long as you can get the probe in there, get it wetted, you can see multiple species, which would otherwise be very difficult to do. And I'll emphasize this again when I come to the conclusions. So let's take a closer look at building models, but this time using robots and computers. And I meant really with computers, I meant partial least squared. So what we're doing, just talk about the model building part, is we're taking advantage of the fact that in the spectra we have very many peaks and varying peaks that can change over different concentrations, and we're using all of these frequencies to build the models in partial least squared. The emphasis really here is on the robotics too, because what I can tell you is when you go to build standards, so we'll talk about calibration set and the test set. Calibration set is the known standard that you work with, and then the test set is something built independently, also using the robot, but then not part of the model itself. And in this case, we're building models for 4 different things: protein, sucrose, trehalose, and arginine. And the next few slides we'll go through quickly all 4 of those analytes of interest. But what I like about using, well, credit to Georgios, my colleague, and Nicole. Georgios is good with the MATLAB in particular, and that's what these next few slides will show. Nicole's good with the robotics. They work together. We're all part of the same engineering technologies team, but this is truly the definition of teamwork. But with the robot, you get the advantage of precision, and also, if you were to make these standards by yourself, you could probably get bored doing it. Certainly I would. Something would happen, an email, something would come in, and you'd get distracted, and pretty soon you'd forget the reagents in which order you added them. So let's take a closer look at the model building process. So here we have a series of slides which shows us building models and testing them against separately prepared samples. So in blue, that's what I meant by the calibration set. These are the defined known concentrations of samples. In this case, it's protein. And then we have prepared 1, 2, 3, 4 different samples here of protein at different concentrations and see how well the model predicts what the protein concentration is. Now, just a little bit more details about the model. This model is actually one model with all 4 components being predicted by that model. And you can see there's a little bit of error, but that's actually, in terms of numbers, most people would be very happy to have a model that has a root mean squared error prediction of about 1 to 2 milligrams per ml. And of course, the more concentrated you go, that percentage of so-called error is even lower, so it works better the more concentrated you get. Now we'll take a look at the other few excipients that are in these examples, and then we'll wrap up with some conclusions. So here's a model built for sucrose. Same principle, start out with a high concentration, a medium, and then no sucrose in the system. And again, all these are varying orthogonally. So we're changing the concentration of sucrose, we're changing the concentration of protein. We're never doing an example where you cut the protein concentration in half and you cut the sucrose concentration in half and you cut the other excipients in half, because that's, in PLS world, that's going to give you a similar response, and you're not going to be able to tell the difference sometimes. So that's why you have to make these so-called orthogonal data sets where they change independently of each other. But again, same concept as shown before, a higher concentration and a couple medium or lower concentrations, and the model is predicting quite reasonably for this particular analyte, sucrose. With trehalose, calibration sets in blue, points in blue, and then predicting the test set. And again, these numbers are something we would be happy to have for a model prediction purpose. Finish up. Last excipient in question, arginine. A little bit more variation here seen in this data set, but again, that's okay. You can build many models, and you can build more samples into your model or fewer samples. It's really up to you to decide what works best for your particular process and what you're trying to trend. I will say it is important to have the components that are in your samples you have to put into your model building. You cannot, for instance, in this example, if we are building a model with these four species of interest, and then we're doing an example earlier where we're changing into phosphate buffered saline, that may not work properly because that peak may show up where some of these other peaks for, let's say, arginine overlap, and that could throw off your prediction very easily. So you're going to have to use the species of interest. And you could build this either with a robot, or you can just use offline samples that you pull from the process and build the model that way. Now, this work shown here is done with MATLAB, but there's no reason why you cannot use the built-in software from the METTLER FTIR. The ICIR has a model building software called IC-Quant, and it's the same idea. You would put in the known concentrations in your calibration set and then use them to predict the test set. You can use Simca, you can use PLS Toolbox, you can use Unscrambler. It's really up to you to pick the type of model building software you want to utilize. Okay, so now this brings me to the conclusions. We're here at the end, and for me, FTIR stands for Fun Time Infrared Spectroscopy. The reason is there's a lot of advantages to this technique that might not be apparent if we were just using offline measurement techniques. First of all, the more concentrated the system gets, the better it works. You will never exceed, at least in my experience, with proteins, you will not exceed the linear range of this detector. It just won't happen. It's got more than enough linear range. Even if you double or triple, I don't even think you could triple the protein concentration from what I showed you before. It still will give a linear response along that range. You don't have to pull a sample from the system. That is a huge selling point for the FTIR. And I'll emphasize it again at the very last bullet point. But just think about how difficult it's going to become to get samples out of the system when it becomes more and more concentrated. And then seeing the process in real time. You could build those same trends I showed earlier with offline data points, but it would require a lot of samples, and you would still be filling in the blanks in between. With the FTIR, we're taking a spectra, let's say every 2 minutes, and we're seeing a trend, and then you can ask questions based upon that trend. This is very much a case where trend is your friend. For modeling, we can do simple semi-quantitative peak trending. As long as you have a couple good reference points, you can probably pick a peak and an area or a peak height and give a trend that is going to be reasonably close to the offline value. If you want more quantitative techniques, you can build more extensive models using partial least squared. And again, that software is built into the METTLER program. I've used Unscrambler. Simca is a good one, PLS Toolbox. It's really up to you to pick the right tool for your application, but the IC-Quant is more than adequate. And you saw earlier we were predicting 4 different analytes of interest using MATLAB in that case, but one model to predict 4 things. And last, my favorite slide in the whole presentation, one technology to rule them all, because this, again, I emphasize how difficult it becomes when you're pulling samples from a viscous mixture. The question comes up, well, how do you pipette it out? Do you have to wipe the pipette tip? How do you dilute it properly? How do you ensure it's mixed properly? If you're doing chromatography, you have to make sure the column itself captures all that protein, and you get the analyte, sucrose, for instance, of interest. You get that through the system, and you can then quantitate it. It's a difficult problem. It's all down to sample handling at that point. But if you have the probe in there, you can gain insights into the process. And more importantly, this is, you can't hide from spectroscopy. That was a phrase a colleague taught me once. You cannot hide from spectroscopy. If it's in there, the FTIR will more than likely see it. And then you can generate trends of 3 different things in the example I showed you before. And it's a very viscous system. And yet, here the FTIR is working. As long as you wet it, you don't have an air bubble on the window, and you get it into a well-mixed portion of the tank. You saw earlier how it wasn't fully mixed, and it required a little bit more effort to get it mixed. But that's the advantage of using the FTIR. So I thank every one of you for your attention, and in a few minutes we'll have questions.